Let's try to save some computational results. Let's look through variables and different variable types that we can use for that. For example, let's say that our variable a equals to 10. What this record means is that the value that has been calculated from the right-hand side of this equation will be assigned to a variable that has symbolic name a. So from now on, whenever we type a, we get value of 10. If we were to modify this to, for example, a equals to 10 plus 5, and run this, we get that the value of a is now 15. So a is a container for that number. These containers can be substituted, obviously, in the equation, so we can type a times 3, and we will get correctly 45 as the result. Similarly, we can type a equal to a plus 1, and we will type a at the end to see the result. This way, we expect a to increase in value by 1 every time we run this line. And as you can see, this is what happens. Hence, a is a mutable variable. Mutable means that it can be changed after the value has been assigned to it for the first time. In this particular case, a is an integer number. In Python, this means it is a big integer value. The reason why it is considered big is because it has no limitation on maximum number that it can represent due to limitation of bitness. So remember that we have talked about bitness of integer numbers in the first part of this lecture. And in Python, that does not really matter. In Python, if you use integer data type, then you will be able to represent any integer number so long as it can fit in your whole RAM. As we can see, our big int has been successfully saved, and it preserved correctly all the numerical positions. And you can see if we take it to the power of 55, we still have all this precision available to us. And if we add just 1 here, it will correctly increment only the last position. This is behavior that you will never see in floating point data type. Floating point data type will start rounding things very early. This is a feature that not many programming languages allow, and Python is almost unique here. And this is very useful feature because if you are going to use integer numbers, for example, to have some precise calculations, then you don't need to think about any rounding errors. However, contrary to that, the size of your floating point variables, for example, an assignment of a equal to 0.5, matters a lot. As we can see right now, it assigned itself correctly, but if we will start adding some digits after dot, and we will add 1 at the very end, you can see that this number is already misrepresented. We cannot have this high precision with floating point numbers in Python. But that's not the worst part. The worst part is that even though we have this 0.5 represented correctly, if we were to take it to the power of 100, we will start getting very interesting results. And to make it fair, let's take 1.0 to the power of 100, which should be 1.0 still. This part works. But if we were taking some smaller number, and this still works. But if we will use scientific notation, for example, 5 times 10 to the power of 119, this number is correctly displayed, but try adding 1 to that. And you can see the number hasn't changed. So it doesn't really matter in this case how many times you will try to add 1. It's not a display feature, it's real that this number has not changed after adding 1. And it doesn't matter how much time you will try to repeat that. And this is the limitation of precision for floating point data types. And if you imagine that you will have a matrix where you will have multiplications and additions together, you will have, for example, 2 elements of matrices that are inputs for matrix multiplications produce very large number, and then you add some constant to that, then you will start losing actual precision of your computations, and that is bad. Now let's discuss drawbacks. Specifically drawbacks of big integer numbers, because, well, why wouldn't you use that if they are so good? Let's say we have two variables. One variable is a, and it is our integer variable, and the other variable b is our floating point variable. And they behave in completely different ways because of their nature. The difference in implementation on the processor side is such that operations on big integers will actually require a lot of extra computational steps, because processor will basically have to split big integer into smaller blocks that fit into operational capacity of a given processor in terms of bit size. And only then it will take computation of every part. And for example, for addition, you will basically have to have one addition per segment instead of one addition for the whole number. In terms of multiplication, you will have time that is proportional to the square root of your parts, because you will have to multiply each with each. And in terms of division, it will be proportional to the cube of the amount of parts, because it will have to implement long division algorithm for that. And basically the problem is that modern processors are not designed to hold these large numbers, so sequential performance will also be affected. If you will try to load this one big integer number into registers, you will figure out that there is not enough register space in the processor. And this means that even parts of operation on these big integer numbers will require your processor to constantly fetch data in and out of the cache. And that's not very good for your performance. On the other hand, floating point numbers are quite flexible. So long as you don't care about loss of precision when you add big numbers to small numbers, which is quite often the case in the real scientific applications, these numbers can become reasonably big, because the exponential part has some amount of digits in it, and this amount covers actually very large numbers. So from the point of physics, you can use floating point numbers for your operations. Just be aware that if you start adding big and small floating point numbers, then you basically discard the small part. And neither the floating point numbers can go to any scale in terms of being large or small. The limitations on the bitness of the exponent will also limit your ability to do that. And once you reach the maximal value of exponent, your floating point number will effectively turn into infinity, or zero if you reach the negative side. These edge cases are defined by floating point convention and vary between programming languages and platforms. And as you can see, there is a constant for infinite number in math, and this is a floating point number actually. So if you will take 1 and you will divide it by math.inf, you will actually get 0, a floating point 0. Another important thing, if you recall the math library and you will try to use any of the functions there, the caveat is that most, if not all, of those math operations are actually operating on floating points. So if you were, for example, compute square root of our big int value here by typing math.sqrt and passing big int as argument, you can see that we got a floating point number, and this floating number is precise up to just this decimal point. After that, we have lost the data. And we will take this number and multiply it by itself. And then we will convert that into an integer representation. And let's say that we want to see the difference between these two numbers. As you can see, these numbers are very different. And this is 10 to the power of 37. So in terms of absolute magnitude, big int is obviously 10 to the power of 53. and here we have only a small fraction of that as an error. So if we were to compare these numbers, they will still be quite big, but there is still this error. And if you start doing a lot of calculations together, then these errors tend to accumulate. Another important basic data type is string. For example, A in double quotes is a string. You can multiply strings by integers, and this results in them being repeated. You can also have more than one character in a string, and it will repeat them sequentially. If you look at this carefully in terms of Python, a string is actually a sequence of characters. Or in terms of Python, this is actually a list. So if we will take this ABC, or let's make it just B times 10. Let's repeat character B. We'll have this list. And let's save it to some string variable. And now this some string can be used as a list. So we can use square brackets to access individual elements of that string. To make it slightly more obvious, let's do it like this. And let's see that our string is ABCDE, ABCDE, and so on. And if we use 1, it will be B. If we take second element, it will be C. Third, D. Fourth, E. And the fifth element will be A again. But as you can see, although this is something similar to a list, we cannot assign any values to it. Also, if your string has only 10 characters and you try access element number 10, you will get an error that string index is out of range, and that is because the indexing starts from 0. So the first element is element 0 and the last element is element 9. And trying accessing any elements outside of that range will result in index error. So as you can see, strings can be defined as normal strings or they can be defined as individual characters. It doesn't really matter. And neither there is difference between single or double quotes. And since Python version 3.6, you can also use special formatting strings. For example, you can prefix string definition with F, and then you can put figure brackets inside. And if you put the name of the variable inside those brackets, then this variable will be formatted as part of this string. And you can see it properly formatted. A's value is 15. We will discuss this a little bit more when we are going to talk about basic input and output in this lecture. But for now, it is important to understand that this is a very easy alternative to use of str function that will actually convert the value of A into a string representation. We will talk about representations later again. And you can see it formatted it correctly. And this line is commented because it starts with sharp. 3 more important built-in functions for Python can be used to convert data types around. So one of them is hex. And this function will take some value and it convert it to hex representation. So you can see it starts with 0x and then the actual hex value. Then float will convert any values that is passed to it, either string or an integer, into a float representation. You can also pass floats. They will be just kept as they are. Conversely, int function can be used to convert values back into integer representation from either float or string, with exception that it cannot convert string that represents actual float, so it has to be just integer here. And if you will try to have dot or comma there, you will get an error. To convert these into integers, you need to have an intermediate step of first converting them to float and only then converting that float to int. And finally, one important note about int function is that it can actually interpret integer numbers in different notations. For example, if you supply base equals 2, then the result of this operation will be 2, because 1, 0 in binary is 2. Similarly, you can type 8, and you will get 8 because 1, 0 in octal system is actually 8. And even you can type here 16 to convert hex number, and 1, 0 in hex is not surprisingly 16. And this would be 20. Finally, in order to convert numbers around, you can also use two useful functions, and they will help you in converting and interpreting some especially binary data. For example, CHR function returns the character that is represented by ASCII code. So let's type 0x30, which is ASCII code for 0, and we get character 0. And 31 is 1, and so on. And the inverse of that is ORT function. This one takes a character, and we can type any character here, and it will get our, in this case, decimal representation of the character code for this character. We can also use some more special characters here. I don't think that I have any on the keyboard, but let's take some random Unicode character from the internet. So if we copy paste this symbol and we paste it here, we can get the Unicode code of that symbol, 9733. And as you can see, that will match to 2605, which is in hex. If we convert this to a hex number, this is the correct value for this star Unicode symbol. So in principle, without even having access to this table, we can do in reverse. We can go and start producing numbers from this hex code using CHR. So this would be our star, some other star, some other symbol, and so on.